Hey there, we're starting Unit 4, and there's a lot going on in Unit 4, lots of graphing and calculator use, and so we're starting at scatter plots. The championship game's on the line between Tinker Toy Tech and City College. Robbie plans to attend Tinker Toy Tech next fall and desperately wants to see the game, which has been sold out for weeks. Surveying the exterior of the stadium, he discovers a small drainage pipe in a brick wall. Looking through the pipe, he has a direct view of the field. The stadium is being prepared for the big game, and a maintenance van is currently blocking the view from the pipe, but the van will be moved prior to the game. The south end of the field is 50 yards from the end of the pipe, and the field runs from north to south. So you can see that there's a diagram here with the pipe, and you can see that there's 50 yards between the end of the pipe and the end zone. All right. The total length of the playing field, including the end zones, is 120 yards. So that's standard, 100 yards for the field, 10 yards for each end zone. The width of the field is 53.3 yards, or 160 feet. The pipe is at the south end of the stadium and at the center of the field in the east-west direction. Investigate how much of the field Robbie will be able to see when he looks through the pipe at the game. So first, we will collect some data. And normally what we would do in the classroom is we would have you stand in front of a wall holding what is simulating a pipe. So think about holding a paper towel tube. And what you would have is you would be simulating a person looking through the brick wall and having a field of view that gets wider and wider as it gets further away from the wall. Clearly, this is a wonderful diagram of me looking through the pipe at the field. I know. Don't be jealous of my artistic skills. It says record the length and diameter of your view tube. And so I had a paper towel tube that was 12.875 inches with a diameter of 1.66 inches. And gather 8 sets of data by measuring 2 distances, your distance from the wall and your width of field of view. So what I had here is a set of data that we had collected in a previous year. When you are 60 inches from the wall, you can see 9.3 inches of field, or 9.3 inches wide of the view. So if you're looking here, what you're going to pretend is that this person's foot is 60 inches away from a wall. So we're going to pretend that there's like a wall here. And from one side that the person can see to the other side of what the person can see, if they are 60 inches away from the wall, the data that we had collected was that they could see 9.3 inches. So from left to right, so you have to imagine this being from left to right, the person could see 9.3 inches wide. And as they walked backward, as this went up, so let's say we're going to go back to being 72 inches from the wall, the 9.3 inches wide that they could see went up to 11.4 inches wide. So every time they stepped back, what they could see was a wider and wider field of view. So this was all the data that we had collected. And it says, make a scatter plot of your data. Describe the association between the width of the field of view and the distance from the wall. If you need a reminder about how to describe associations, there was a good math notes box in lesson 221. So what I did was I went ahead and I graphed the points of the scatter plot. So here we go. And you'll notice that I put distance from wall along the bottom on the x-axis. That's because the control variable goes on the x-axis, and I have control of how far I am from the wall. The dependent variable, the width of field of view, goes on the y-axis because how wide of a view I have is dependent on how far I stood from the wall. If I chose to back up further, then my width of field of view got wider. If I chose to get closer to the wall, then my width of field of view got smaller. All right, so that is my set of data on my scatter plot. I plotted the 1, 2, 3, 4, 5, 6, 7, 8 pieces of data that we collected. So you'll notice there are 8 points on the scatter plot. Now, what type of association do you see? It is strong, meaning that the dots line up pretty closely to a straight line. It's positive, meaning that they are going up to the right. And it's linear, meaning that they appear to be in a straight line pattern, not curved. So we would say that it is a strong, positive, linear association. Draw a line of best fit. So let's review how to draw a line of best fit. when we put our graph, our scatter plot in front of us, in order to draw a line of best fit, we want to make sure that we follow the points. So we're not like aiming for the origin, because the origin is not following the points. You'll notice that the points seem to be up much higher than that. We also want to try to split the data in half. So we had 8 points. We're kind of aiming for 4 above and 4 below, and we want the line to stay as close to those points as possible. So something like this. Now, because I just did this live, you'll notice that maybe it doesn't match up perfectly with the hard copy of the notes, and that's okay. Scatter plots are always going to be slightly different when you go to draw your fitted line. And they're not perfect. None of them are perfect when we draw them by hand. We are, during this chapter, going to learn how to get the line of best fit using a calculator, which is going to be a mathematical process instead of a visual guessing process. All right, so I've got my line of best fit, and I need to make an equation for the line of best fit. So I need to pick a couple points that are good points, points that look like they're right on the crosshairs of a set of numbers that work nicely. So I might pick this point here, which is 150.22. Now your points might be different because your scatter plot, your fitted line might be a little bit different than mine. So you might pick different points. Let's see, that was a good one. And do I see another? You don't want to pick points that are too close to each other. That's another thing. You want to make sure that there's a little bit of room between them. So I wouldn't want to pick this one, which is really close. So I might go down here and say, yeah, I mean, this is pretty close to being on the crosshairs. I'll go with 85.13. It's not perfect, but it's okay. It's as close, I think, as I'm going to get. So now, in order to find my equation for the line of best fit, I need to start with the slope. So I'm going to do y2 minus y1 over x2 minus x1. And I'm going to find the slope of my fitted line. Now, my fitted line could be steeper or less steep than yours. 22 minus 13 is 9, and 150 minus 85 is 65. So I'm going to have 9/65. And I am not going to want to work with that. That's not very friendly. So I'm going to go with approximately 0.1. And in this case, I got 138. So I'll go approximately 0.14. You'll notice on the hard copy of the notes, I had 0.13. So apparently when I drew it last year, I had a line that was slightly more shallow. So now I'm going to go with y equals 0.14x plus b. I'm going to plug one of those two coordinates in and say if y is 22, 0.14 times the x value of 150 plus b. I chose to use this point. You can use either point. Not going to make a difference because they're on the same line. So when I multiply, I get 22 equals 21 plus b, and I would subtract 21 from both sides, and this came out very nicely that 1 equals b. So my y-intercept for this particular line is a 1, so I would say y equals 0.14x plus 1 is the equation for my fitted line. Excuse me. Draw a line of best fit. We did that. What is the equation? So my line of best fit was y equals 0.14x plus 1. And some people will even, instead of putting an equal there, use an approximately, just because we had to round the 0.184615 to approximately 0.14. All right. So what do the slope and y-intercept represent in context? In context, the slope is saying the 0.14 is that there's a 0.14 inch increase in the width of the field of view for every 1 inch I move away from the wall. So what we're saying is 0.14 over 1. That the rise, and in this case on the y-axis, we had width of field of view, that for every 0.14 inches that I gain in my width of field of view, I have to walk 1 inch away from the wall, distance from wall. And that's because it's rise over run, or it's the change in y over the change in x. So if I want to increase my width of field of view, every time I move 1 inch away from the wall, I gain 0.14 inches wider of a field of view in front of me. The y-intercept. Now, this is an interesting one because it doesn't come out perfectly, and it never does because, again, scatter plots have human error in them. This is supposed to be the width of the field of view at 0 inches from the wall. And what it should match the diameter of the tube. And ours is actually pretty close. The diameter of our tube was 1.66 inches. So what they're saying is if you had the tube right up against a flat surface, you should be able to see 1.66 inches wide because you should be able to see the whole tube width. And we got approximately 1 inch, which was slightly smaller, but actually a really good prediction as far as scatter plots go and real world data. That's really close. All right, so I'm going to stop this video at the front. There's a lot to take in just on the process and getting the scatter plot and what it looks like. So if you need to take a break, that's fine. And then the second video is going to be continuing on the back side. What do we do with this data?